geometric sequence look like? A is the first term, A times R is the second term, A times R squared is the third term, A times R to the third. Can anyone give us the next term? So this is when n is 1, this is when n is 2, this is when n is 3, this is when n is 4. Yes, comma, dot, dot, dot. Can anyone give us the generic term? Minus 1. 1, power 0. 2, power 1. 3, power 2. 4, power 3. Is this clear? Dot, 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 dot. This has a common ratio. Common ratio. What is the common ratio? Is the quantity I multiply the previous term by to get the next term. So we multiply this by what?
R to 0.
By R. They're all the same. We multiply this by R to get this. We multiply this by
R
to get this. We multiply this by to get this, and so on and so forth. So that is the common ratio, which is R. Let's play with this for a moment before we look at the sum of the partial sums. The nth term of a sequence is given. Find the first 5 terms. What is the common ratio? And graph it. Graph the terms you found so we can do this with the calculator. Okay, so let's look at problem 8, in which I have an equals 3. Oh, this is 6, I'm sorry. 3 times negative 4 raised to negative n minus 1, and we are on page 806. Page 806. So we're asked to find the nth term is given. Find the first 5 terms of the sequence. And what is the common ratio? So A1, let's find the first two, and then we can plug it in the calculator and find the rest. So what would you say about A1?
Or negative 40 is 0.
Yes. So this is excellent. A2 will be 3 multiplied by negative 4. So this will be negative 12. Okay, let's look at also A3. So this will be 3 multiplied by
16.
awesome, 48. And we can continue forever, correct? Okay, can anyone give us the ratio? What did I multiply A1 by to get A2? Negative 4. What did I multiply A2 by to get A3?
Negative 4.
Correct. And that is the common ratio. So I don't even have to look at the general term anymore, because now I already know how to find A4. What would be A4?
Multiply that by negative 4.
48 by negative 4. Correct. Okay. What is the common ratio? And then graphing the terms, I can graph the terms by hand. Let's just graph one by hand. So when n is 1, I have 3. This is n, and this is an now. When n is 1, I have 3. When n is 2, I have negative 12. So bear with me and say that this is negative 12. When n is 3, I have 48. And the terms we say are oscillating between positive and negative. They are going positive, negative, positive. Okay, very good. Find the nth term of the geometric sequence with given first term A and common ratio R. So we are looking at problem 10. So we are given A equals negative 6 and R equals 3. They are asking us to find the generic term. The generic term is A multiplied by R raised to n minus 1. So what is A?
6.
Good. Multiplied by r. How much is r?
3.
Raised to which power?
0. And one exponent.
That's it. Don't be tempted to multiply because there is a power there. Determine whether the sequence is geometric. If it is geometric, find the common ratio. Let's say 16. We have 27, we have -9, we have 3, we have -1. Is this sequence geometric? If it is, find the common ratio.
So
What do I multiply the first term by to hopefully get the second term? Okay. What will I multiply -9 by to hopefully get the third term?
Negative 1/3.
What do I multiply 3 by to get the fourth term?
Negative 1/3.
So then what is the common ratio?
Negative 1/3.
Awesome. Will I say then that this is indeed a geometric sequence?
Yes.
Yes, it is a geometric sequence because the second term was obtained by multiplying the first term by the same number that is used to determine the third term by multiplying the common ratio with the second term. So this is geometric, and the common ratio is -1/3. So geometric, and the common ratio is -1/3. Any questions?
So for a number like 15, that wouldn't be geometric.
Let's take a look. I don't know. Let's take a look. 15. Good pick. So we have 3, 3 over 2, 3 over 4, 3 over 8, dot, dot, dot. Okay. So I don't know if this is geometric or not, but I will divide 3/2 by 3 and see what happens. I will divide 3/4 by 3/2 and see what happens. I will divide 3/8 by 3/4 and see what happens. If all these three numbers are the same number, what will I conclude?
It's geometric.
Geometric, and the common ratio is blah, blah, blah. What if I don't get the same number?
Then it's not geometric.
And it's not geometric. Okay, so this is 3 over 1. So 3 over 2 times 1 over 3 is 1/2. If this one is not 1/2, I don't have to determine the third one. So let's look. 3 over 4 times 2 over 3. Ah, it says 1/2. And then I'll calculate that one just to make sure. 3 over 8 times 4 over 3. Ah, 1/2. So what do I conclude about this?
Geometric.
It's geometric. And the common ratio is 1/2. Awesome. Very good pick. Okay, moving on. Find the first 5 terms of the sequence and determine whether it is geometric. Okay, so let's look at 22. A(n) equals 4 plus 3 to the n. If it is geometric, find the common ratio and expresses in the nth term, blah, blah, blah. Okay, so it says find the first few terms, the first 5 terms. So how much is A1?
7.
Good. How much is A2?
13.
Awesome. How much is A3?
31.
Yes. How much is A4? Awesome. 3 to the 4th is 81.
85.
And A5, 3 to the 5th is 81, 243, 247. So 13 divided by 7, will that equal, so 13 over 7, does it equal 31 over 13? Does it equal 85 over 31? Does it equal 247 over 85? Let's grab the calculator and just divide just the first and the second, and that's enough. So, of course not, but let's do that. 31 divided by 13. No. So, what do we conclude about this sequence? Not geometric. It is a sequence, but not a geometric sequence. Awesome. Determine the common ratio, the fifth term, and the nth term of the geometric sequence. 32 caught my eye. We have negative 8, negative 2, negative 1/2, negative 1/8, dot, dot, dot. So they want the common ratio, the fifth term, and the nth term. So the common ratio, A5 and AN. Okay, so what do I multiply negative 8 by to get negative 2? I still have to check. What do I multiply negative 2 by to get negative 1/2? Good. What do I multiply negative 1/2 by to get negative 1/4? Negative 1/8. That's it. So obviously this is geometric and it has a common ratio of 1/4. Okay, so now can anyone give us A5?
130.
Yes, negative 1/32. Awesome. So now we would like to determine this AN. And remember, AN is the common ratio raised to n minus 1 multiplied by A. A times R to n minus 1. So AN equals. Let's leave the A for a second. So what is R? Raised to which power? Good. And now let's analyze what we should put in front. So that this generic term, when I plug in 1, I get negative 8. When in this generic term I plug in 2, I get negative 2. When I plug in here 3, I get negative 1/2, and so on and so forth. It has to work. Okay, good. So, first of all terms have to be negative, right? Okay, what is our A? Because remember, this is A times R, A times R squared, A times R cubed, and so on and so forth. So what do I have to write as A? Negative 8. So now let's check. Just to make sure that we didn't miss anything. So when n is 1, this is 0, and this is 1. Do I get negative 8?
Yes.
When n is 2, I have 2 minus 1, which is 1. Negative 8 times 1/4, is that negative 2?
Yes.
When n is 3, 3 minus 1 is 2. 1/4 times 1/4 is 1/16. Negative 8 times 1/16, is that negative 1/2? Therefore, this is the generic term of the geometric sequence. Okay. Now, the last thing that we have to look at, let's find the sum and then the partial sums, and it's done. So let's look first at defining the sum, like 49. The sum from k equals 0. Now they put k in there. 3 1/2 raised to k, and let's do this with a graphing calculator. We just learned a new way from Shane. Thank you, Shane.
You're welcome.
So I go to second and quit, and I'm going to be lazy, and I'm just going to copy what he just told us to do. And I'm going to say that n goes from 0 this time, and it goes to 10. Okay. And now I have 3 is outside of parentheses. It won't allow me to put it outside. Okay, that's fine. 3. And now in parentheses, 0.5 caret raised to power n. Okay. So I have 3 and 0.5 raised to power n. That's it. And it goes from 0 to 10, and I press enter. And I got 5.99707, 5.997070313. Did you get the same thing?
Mhm.
Awesome. Okay. Partial sums. Nothing new here. S1 is A1, S2 is A1 plus A2, and so on and so forth. So Sn is the sum from A, R to n minus 1 from k equals 1 through n. And that is, we can prove it, but I'd rather I'll show you how to prove it. We're not going to do it. I'm not going to ask you to. You can read this, what they did here. So they wrote the sum, and they also determined, after they wrote the sum, they multiplied both sides by A, and they multiplied both sides by R, and they added the terms. And that's how they came up with this. So then this is A, 1 minus R to the n power over 1 minus R. If we look at A times R squared, dot, 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 infinite terms, this is no longer called a sequence, but it's called an infinite series. Infinite. Geometric. Because we didn't stop at n. We go on forever. Geometric series. Only because it has infinitely many terms. If that's the case, the sum from k equals 1 through infinity now of A, R to k minus 1, this term will disappear, and we only have A divided by 1 minus R. A series, geometric infinite series. That's what I meant. Geometric infinite series converges if the absolute value of the common ratio is less than or equal to 1. I'll explain the word converges in a second. And diverges if the absolute value of R is greater than 1. So what does converge and diverge, what do they mean?
Come together a little bit.
Nope. No. If I'm able to add the sum of all terms of an infinite series, if I'm able to add them and say the sum is 5, then the infinite series are called convergent. If you say add the sum of these infinite series, and I say I can give you the sum, it could possibly be infinity, I can determine the sum. It's not a finite number. I cannot say it's 10 or 100 or 10 million. It's not a finite number. Then we say that the series is divergent. If we can find the sum, then it's convergent. If the sum is infinite, it's divergent. And this is always true as long as we are talking about geometric infinite series, if the ratio is a number between -1 and 1, then the series will be convergent. If the common ratio is a number like from 1.2 and above, or greater than 1, then the series, the geometric infinite series, is divergent. Okay, so let's look at the last two problems here. Find the partial sums Sn of the geometric sequence that satisfies the given conditions. So let's take a look. 44. We have A equals 2/3. We have R equals 1/3. And we have N equals 4. Since N, this is not a sequence, since we are given N equals 4, this is not an infinite series. So we are really asked to find the sum from I equals 1 through what?
4.
Awesome. From what? 2/3. 1/3 raised to I, no, careful, -1. So let's put in the graphing calculator. Again, I'm using what we already have, second and entry. So we start at 1. It doesn't want. Okay. Okay, 1. And it goes to 4. And now in front I have 2 divided by 3 in parentheses, careful. And then I have another parenthesis where I have 1 divided by 3, close the parenthesis, to power n minus 1. I like parentheses, you know that already, n minus 1. And then close this parenthesis and close the outside. And it's done. And the answer is 0.98765. Look at that. Look at that. Awesome. Okay. Uh, 37. The first term of a geometric sequence is 8. A equals 8. The first term. And the second term is 4. Find the fifth term. The first term of a geometric sequence is 8, and the second term is 4. I want to find A5. What do I need to determine?
Common ratio.
Good. What is the common ratio? What do I multiply A1 by to get A2? A1 by to get A2, I multiply by 1/2. So therefore, A5 will be A times R to 5 minus 1.
So
8 times 1/2 raised to the 4th power indeed. So this is 8 divided by 2 to the 4th is 32. So this is 1/4. Yeah. Right? I simplify by 8. Is that okay? So A5 is 1/4. Determine whether the infinite geometric series is convergent or divergent. Okay, so let's look at 51. In 51 we have 1 plus 1/3 plus 1/9 plus 1/27 plus ... If it is convergent, find its sum. What do I have to determine in order to establish whether this infinite series is convergent or divergent? I have to determine it all depends on the common ratio, correct. What do I multiply 1 by to get 1/3?
1/3.
What do I multiply 1/3 by to get 1/9?
1/3.
What do I multiply 1/9 by to get 1/27? So then obviously the common ratio is 1/3. If this number is less than or equal to 1 in absolute value, because it can be positive or negative, then the geometric series converges. Is it?
Yes.
Convergent. In which case, I can determine the sum.
So that's all you have to do is find R to find.
That's it. So it's convergent. And we are told if it is convergent, find its sum. The formula for the convergent of an infinite geometric series is A divided by 1 minus R. How much is A, which is the first term?
One.
How much is 1 minus R? Minus 1 minus 1/3?
1/3.
Yes. Very good. So it's 1/2. So the sum is 3/2. Is a number. I can give it to you because the infinite geometric series is convergent. Let's also look at 54. Same question in 54. 2/5 plus 4/25 plus 8/125 plus ... Common ratio is 2/5. Is 2/5 in absolute value less than or equal to 1?
Yes.
So the infinite geometric series is convergent. Convergent infinite geometric series. Good. So then I can find the sum.
So 2/5.
2/5 over 1 minus
2/5.
2/5. So 2/5, 1 minus 2/5 is 3/5. So the answer is 2/3. Any questions?
Look at number 40.
Yes, of course. Number 40. Where is it? The common ratio in a geometric sequence is 3/2. So common ratio in a geometric sequence is 3/2. And the fifth term is 1. A5 is 1. Find the first 3 terms. Awesome. So I know that A5 must be written how? A multiplied by 3/2 raised to which power? Which power? So the generic term of geometric sequence n minus 1, which is n is 5, 4. Very good. And this, I am told, equals 1. What can I determine from here?
You solve for A.
Exactly. This is the equation in which I solve for A. So this is A multiplied by 81/16 equals 1. So then A equals 16/81. So we are asked to find, one more time, the first 3 terms. So now the general term is 16/81 multiplied by 3/2 raised to n minus 1. I determined what I did not have, which is A. So just give me 1. So let's say just give me A1. What would you say?
16/81.
multiplied by, yes, which is
3x.
1. Perfect. Give me A2. 16 over 81 multiplied by 2 minus 1,
Which is 3x.
3 halves. So I will simplify, and I get 8 divided by 27. And in the same way, I determine A3 and A4. Any questions? Any questions?
So when I'm putting 154 into the calculator, I got a different answer.
54.
Yeah.
When you added,
So when I did 2/5 divided by 1 minus 2/5.
oh, you mean here?
Yeah, the last one. Yeah, I've done.
So this is 3/5. But did you put infinity? We are adding all terms. This is the sum of the infinite geometric series. Did you put infinity? Does it allow you to put infinity in there? I doubt. I don't know how. Because we are adding here the sum of the infinite series. If it doesn't allow you to put the upper limit as infinity, then you cannot calculate with the graphing calculator. Is that clear?
Okay.
That's the formula. So it's A divided by 1 minus R for the infinite. For the infinite. I don't know if the calculator will be able to do this for infinite, because we are adding all possible terms of the series. But if you stop at a different number, then you'll have a different number as a result. Even if you stop at 100 or even at 10,000. Who knows? Maybe if you put it as it's a good point you're making. If you put it as a function, if you put it here as a function, and we can do that. We have the generic term. What is a generic term? The generic term is 2/5. What is it? 2/5 and 2/5 raised to n minus 1. Okay, let's do that. So in parentheses, 2 divided by 5. Awesome idea. Close. And in parentheses, 2 divided by 5 to power n minus 1. Awesome. Good. So now let's go to second table and put in 100. What did we get as the sum? 2/3, which is 0.67. Ugh. Okay, then let me look again. 2/5, 2/5, 2/5 minus 1. Two over 3. Yeah. You cannot even calculate. I don't know. My calculator is frozen.
That's fine.
But this is what I want. I need to add up all the infinite terms.